Right. I want to thank you for the opportunity to speak tonight. I want to start out this presentation with a slide that might be whimsical or it might actually hold some truth. I'm not really sure, but to first order, society's wealth is somewhat proportional to its availability of cheap energy. And you can kind of understand that relationship if you look at the energy that went into obtaining oil in the 1860s, 1840s, 1830s, even back to 1819. Essentially, removing oil from a whale was a very difficult way to get a small amount of oil. It took 4 years, 35 men, and each voyage was worth about $5 million, and I'm not sure how many actually successfully returned. If you compare that to the discovery of mineral oil in Titusville in 1861, you can see that 60,000 liters produced a day is a much more efficient way of obtaining oil. And initially, of course, mineral oil was an enormous mystery to people. They had no idea where it came from. It took many years to understand this source of oil. Now you contrast that with George Mitchell's effort in the Barnett Shale. For a decade, this guy drilled hopelessly poor reservoir rocks and somehow managed to bring this unconventional revolution to Texas and to the United States. An amazing sort of turn of events and an amazing new technology. Gas shale in the United States is arguably turning the economy around. It's playing an incredibly important role in a number of both the economy and environmental movement. I'm not sure which way the environmental movement's going there at the moment, but it's playing a role, that's for sure. Gas production in the U.S. from unconventional sources has increased 42% since 2005. Domestic oil production has increased 52% there. Imports of oil have fallen 28%. Now, that's a very important number in the U.S., given its interesting geopolitical situations in the last several decades. Fascinatingly, CO2 emissions have also fallen 10% since 2005. That's partially because of the recession, but it's also partially because of a transference of gas from coal. Some would say the economic recovery of the U.S., and I was just there yesterday, and it's an expensive country these days, it's really coming back quickly, is associated with the unconventional boom. If you look at gas production in the United States, it's increasing compared to the fall in coal, and that's good news because coal emits significantly more CO2 than burning natural gas for the same amount of power. Interestingly, too, trends expected for gas production, gas import in other countries, so importing fractional percentage of use of gas and oil. The United States actually will be going in reverse, and anticipated by 2035 it will be a net exporter of oil and gas. An extraordinary outcome, at least gas, maybe not oil, but an extraordinary outcome for a country that had a very significant amount of gas and oil import prior to that. The U.S. is riddled now with unconventional wells. Parts of the country are, once wilderness areas, are unrecognizable to me. This kind of very intensive drilling has led to approximately 150,000 wells across the country, horizontal wells, that is, going after unconventional resources. This is an enormous amount of investment occurring, particularly if you consider that only 25% of these will be successful. Most of these won't recover their costs. 5% of those wells that are successful pay for all of the duds. This is kind of like the birth of mineral oil in Titusville. We really have a very poor understanding geologically how this system works. The engineers are working hard to make it happen, but geologically we're significantly lagging behind. The world is following suit, and everybody's quickly looking for their potential fields. Argentina, Australia here. China has enormous potential unconventional reserves. The U.S. also, of course. So Australia is in hot pursuit of this idea, and the estimates in Australia are not exactly nailed down yet, but to say the least, I would suppose, there is a potential for 350 trillion cubic feet. And this would provide approximately 200 years worth of reserves at the 1.8 TCF we use today. There's very limited production. Colin might argue with this if I say no production. You feel free. It's very close to no production from unconventionals. Although I might suggest that the Cooper Basin is one of the pioneer unconventional basins in the world and has been operating as one since the 60s, but that's my own personal take on it. Australia is very remote. The basins in Australia are very remote, and it's very expensive to drill here. Mistakes cost a lot of money. Some of the wells, the exploration wells, are up around $4 million. So Australia is lagging a little bit because of that. The resource still remains ill-defined. Even in this slide from the U.S. Department of Energy, South Australia doesn't particularly feature. The Cooper Basin people know about, but the Arkaringa Basin they don't. The Arkaringa Basin to me looks very exciting as a prospective unconventional source. And the Otway down here is also an area of active investigation. So even with these sort of up-to-date slides, there are still new things coming on. So what is this thing called unconventional? What is conventional gas and what is conventional oil? Conventional gas and oil have a very well-understood pattern. Oil and gas are buoyant, so they rise from a gas-rich source bed. So this is a source bed that has ancient organic matter in it that's slightly heated, and it emits gas and oil as the molecules break down. So initially, this material looks like something biological, but with heat and time, it becomes a gas or an oil, a geological material that migrates, and it gets caught beneath a seal. Now, a seal is a very fine-grained rock that has low porosity and permeability, something like a clay. Seal is what you might find in a landfill as a smectitic clay or something like that, and it's folded. So there's an element of folding, there's an element of heating, there's an element of organic deposition, and all these things are very complicated, and they all have to be perfectly timed, because if the fold doesn't exist when the oil migrates, it goes straight to the surface and comes out of seeps. So in order to capture this and preserve it, all the elements of timing and the reservoir rocks have to be right. There has to be a reservoir that can capture and be producible. So all these things have to work together to get this very special circumstance of conventional oil and gas. But contrast that with unconventional. Here you're just drilling the source rock that is slightly mature and pulling the gas straight out of it that's adsorbed somehow in the source rock. So here you're just capturing it directly. You don't have the vagaries of the geologic system, the folding, the heating that's necessary in the conventional. It's much, much simpler. So for this particular shale gas system, we're looking directly at the rocks that were deposited initially with organic matter. Now, there are other unconventionals too, tight sand gases. This is common in the Cooper Basin. These are gases that accumulate and are trapped by cements. Now, cements are something that happens in a reservoir. They're called diagenetic processes, and they can act to capture the gas within a sandstone unit. You may be familiar with coal bed methane. That's another unconventional approach, and that's essentially gas that's produced from the breakdown of coals and trapped within the coals. I'm not going to be speaking much about that today. That's not really something that we will see in South Australia. It's not appropriate here because these coal beds are not at the right depth and they don't generate gas that we know of. I'll be speaking mostly about these gas shales because that's what are most common here in South Australia. What's so different about this is a conventional reservoir. The oil and gas, water, all accumulate in the spaces in between the sand grains here. And here's a thin section micrograph of a sandstone. And you can see these are little quartz pebbles, and there's space in between, and this is where the gas and oil accumulate. That's about 1 millimeter. And I put this very strange reference up here, width of a human hair, to give you a sense of what the actual scale is. So we'll follow that through. So human hair is about 40 microns, 40 micrometers. There's 1,000 microns in 1 millimeter. And we're going to follow that through as we look at what that means for these very fine-grained rocks where we find these sandstones, find these unconventional resources. Now, this is looking at a core called Encounter 1. It comes from the Cooper Basin. This was beach energy splashed into the unconventional exploration. And you can see it's pretty dull. It's just black, maybe a little bit of gray, laminated. The core goes up, and it's pretty dull-looking stuff. But there's some lamination there. I guess that means something. But then, when we use a scanning electron microscope, because that's the only way we can image these very fine-grained rocks, optically we can't see these things. The grains are too small. And here we have 100 micrometers. So that's 1/10 of a millimeter. And here's the human hair now. It's gotten a little larger. And you can see the grains, kind of like the sand grains in the last slide, but much, much smaller now. And here is actually the petroleum. That's some bitumen or oil that's accumulated in that porosity. Now you can see that that porosity, those holes are not really connected to each other, and it's kind of hard to understand exactly how that communicates and can be drawn to a well, but we'll talk about that a little bit more in a second. And again, there's that human hair. Now this is the coarsest grained unconventional I've personally looked at. Let's look at some examples from the United States now. These are much, much more impressive in terms of what this means for production. These are University of Adelaide students, Lisa Baruch and Sam Fraser. Sam works for Santos now, and Lisa's just finishing her PhD. And they're looking at the classics here. This is the Eagle Ford Formation in West Texas, and this is the Woodford Shale in Oklahoma. They're over in the U.S. trying to get a sense of what does a successful gas play look like in an unconventional rock. And these are exposed on the edge of the basins. Basically, the oil companies are drilling these further to the east in the case of the Eagle Ford and south in the case of the Woodford. When we look at these images, now we're using the power of postdoc Dr. Stefan Lohr, who's using a transmission electron microscope here to image what these grains in the Woodford Shale look like. Now, here's your human hair. It's a little wider than it was in the last image because that's only 1 micron. These are tiny, tiny features, very small, and the organic matter and oils are intercalated within this material. Now we'll look a little closer. We're going to zoom into this box. Now we're at 200 nanometers. A nanometer is a millionth of a millimeter. And we still don't see pores or organic matter. Now we're at 50 nanometers. A water molecule is about 1 nanometer. So almost down to molecular scales here. And we still don't see the organic matter, even though it's in there. There is no communication possible between these little pores. We can't even see the oil. This is how technically difficult it is to understand this problem. How are we moving this stuff around in these reservoirs? Very hard to understand. We used to think of these as seals. Now we're using them as reservoirs somehow. So George Mitchell and others, actually people have been fracking in the Cooper Basin again since the 1960s, so it's not entirely new, stimulating reservoirs, but they experimented around with different materials, fluids, and proppants. Colin's going to talk a lot more about that, and identified that fracturing somehow created communication that allowed these gases to escape from these very, very fine-grained rocks in these very small pores. So in order to do this, they pump very high-pressure fracking fluids. I'm not going to talk about that. I'll save that. And large volumes of those. This thing just, oh, there we go. 8 to 52 million liters for a single well, at least in the U.S. And essentially, this creates microseismic events, little earthquakes. Earthquakes that are about the same as dropping a gallon jug of milk onto the ground from the counter that cause faults to move just ever so slightly and allow these fractures to form that are then filled with something called proppant, which is sitting there. I won't talk about that. And that holds these little fractures open. And somehow, this allows these areas to communicate with the well. But bear in mind, they're spaced, little fractures are spaced about meters apart, and the actual pores are at the nanometer scale. Somehow, this doesn't make sense, and we don't know why, and we're trying to understand that right now. That's where our research lies. Okay. So I'm going to fast forward here. Oops, I'm going to go back one slide. So where are we with this in terms of water? So the risks to water that we see are from that fracking fluid that we pump down and its potential to communicate upward to the drinking water and aquifers. But in shale gas, this is a very, very small risk because essentially there's thousands of meters of separation between the shale formations that have to be under enough pressure and temperature to generate gas and the actual aquifers that we utilize to drink from. So that's a pretty small risk. But what isn't a small risk is the utilization of the water that we find that we must use to pump into these wells. Okay. I'd like to talk briefly, too, about the atmospheric risk. Now, this is something that our group works a lot on, and we work on this fugitive emission issue. I'm not going to deal with the air pollution situation. That's just associated with trucking and infrastructure. But fugitive emissions may be a really serious question. And fugitive emissions are gases that escape from wells when they're drilled and subsequently after they're produced from infrastructure. This has been very topical lately because methane is probably one of the most important greenhouse gases in terms of our ability to regulate it. It's also 1/4 of the total greenhouse forcing the world today, and it's increasing rapidly through time. Some have attributed that recent increase with development of gas, unconventional gas in the U.S. And recent studies have suggested that significant emissions of methane from wells are potentially providing more greenhouse gases than if we burned just coal in itself. So that was a recent study by Cornell University. And essentially, the problem with methane is it has a 33-time or 40-time increase in CO2 efficiency in greenhouse warming than CO2. So, recent technology allows us now to go and measure the amount of methane that's lost in these systems. Prior to that, we really had no idea. But new technology using cavity ring-down spectrometers make this possible. And this is a project with Dr. Mike Hatchett at the university. And he's working with this thing called a Picaro. And Picaro captures samples as we drive and allows us to measure parts per billion changes in methane concentrations. This technology was employed recently by Southern Cross University's study, and it was used to suggest that CSG fields, coal seam gas fields, in Queensland were associated with anomalous releases of methane to the atmosphere, and thus the idea that somehow gas could be a bridging fuel was not a valid idea, and that actually represented a threat to the environment. When we reproduced the same study, we found that actually there's a significant amount of methane that's being emitted naturally, and these fields are associated actually with natural seeps, and that's how they're initially found in many cases. So natural seeps can account for many of the emissions away from the fields that are being drilled. So each one of these little yellow circles is a well, and you can see there are concentrated values higher than background, which is about 1.8 parts per million. But as we get away from those, we still see very high values. The question we need to ask and resolve before we make conclusions about whether fugitive emissions were really threatening us is whether we understand the background levels well enough, and we need to place those in context with other sources of methane. For example, this feedlot is 3 or 4 times the highest concentration we saw in any of the CSG measurements we've taken near any fields. I guess the take on this ultimately is we have so much we need to understand about these systems. They're very technically challenging. They have a great deal of potential. We're concerned about the environmental costs. We see them as a potential bridge between renewables and coal, but we need to understand whether that actually is the case through measurement and objective study, rather than allowing this into the public debate where it's much more politicized and much more inflamed. This isn't about anything other than making the measurements and trying to decide if indeed we're losing significant methane from these wells. If we can't fix those problems, we need to understand that. And we also need to understand how much of this can we actually produce before we are in a position where we're threatening CO2 or greenhouse gas emissions substantially.